In this chapter, we are going to go over the network layer, which is part of chapter 5. Please make sure that you do read this lecture before you actually continue on to the rest of the homework. The network layer is concerned with getting packets from the source all the way to the destination. Getting to the destination may require making many hoops, and intermediate routers along the way. This function clearly contrasts with that of the data link layer, which has more modest goal of just moving frames from one end of the wire to the other. Though, the network layer is the slowest layer that deals with end-to-end transmission. So the network layer, as we discussed, is responsible for delivering the packets between the endpoints and multiple links. There are, of course, some design issues, okay? Of course, you basically include service provided to the transport layer in the internal design of the network, okay? So you got the store and forward packet switching, okay? Which if you look on your page 356 of your book on figure 5-1, it actually gives you an idea and explains the details of the network layer. In this context, it says the major components of the network are the ISPs. You got connectionless service, diagrams, virtual circuit, and comparison. We're going to go into this in detail next. So store and forward packet switching. Again, on page 356, you can actually get an idea of how this works. And basically, it's hosts that are sent packets into the network and the packets are forwarded by routers. Routers treat packets as messages, which is basically receiving, storing them, and then forwarding them based on how the message is addressed. For completeness, it is the process running on the host that sends the packet into the network and then receives the packets at the destination. Okay? So a host with a packet to send the transmit to the nearest router either on its LAN or over point-to-point to the ISP. The packet is stored there until it has fully arrived and then the link has finished its processing before verifying the checksum. Then it is forwarded to the next router along the path until it reaches the destination host where it is delivered. This mechanism is stored in forward packet switching as we've seen in previously. Okay, the next one is the connectionless service diagram, and for this one you can look on page 358 under figure 5-2 and it actually gives you an idea of how this works. So this model is like a postal service. Each letter is sent through the network independently. A datagram is a packet that contains an absolute destination address. Routers need to only look up the destination address in a table to find the outgoing line to send the packet its way. If connectionless service is offered, packets are injected into the network individually and then routed independently to each other. No advanced setup is needed. In this context, the packets are frequently called datagrams, as we know, and the network is called a datagram network. Okay? If the connection-oriented service is used, a path from the service router all the way to the destination router must be established before any data packets can be sent. This connection is called a virtual circuit in an analogy with the physical circuit set up by telephone system, and the network is called a virtual circuit network. This model is like a telephone network, which is packets is forwarded along the virtual circuit, just as we were discussing, and the packets contain tags that are not full addresses. They only need to be unique at the given link and though are rewritten at each router from an incoming tag to an outgoing tag. The virtual circuit is set up with a tag mapping along the entire path. Then packets are sent along it. The packets will though all follow the same path and arrive in order. On page 361 of your book for figure 5-4, you can actually have a diagram and it actually compares the different types of issues and how the datagram works with the virtual circuit network. This diagram will actually give you an idea of how these things work, and basically where you have the major issues that are listed, and then the purist that could probably find in the counterexample for every figure. Next, we're going to look at the routing algorithms. This is very important part that you all need to look at very closely. And this actually starts on your book on page 362 if you want to follow with your book. Okay? Routing is the process of discovering network paths. In other ways, how or where are you going to be sending this? Model the network as a graph of nodes, decide what to optimize, and then update the routes for changes in topology. Forwarding is the sending of packets along that path. Distinguish routing from forwarding. So we focus on adapted routing schemes that update routes and response to failures. Some traffic-aware schemes also adapt to changes in traffic, but we do not consider them as an algorithm. For the graph, the traffic demands A to A, B to B, C to C, and X to X. What will be fair? For each flow to get the same amount of bandwidth, if all network links have a unit capacity, then we would give each flow half a unit of capacity. So the total network traffic is then 2 units. So if we gave X to X, flow no bandwidth, then we could give each other the 3 flow 1 unit. The total network traffic is then 3 units. So it's more efficient, but it's not fair. So we will have to decide what we want to optimize. So the optimality principle, okay? If a portion of the best path is not the best path, then there is something better. Substitute this better portion and you could have a better overall path, which cannot be the case in the overall path is a best path. So in each portion of the best path is also the best path. The union of them is to a router is a tree called a sync tree, okay? Which best means fewest hoops is an example. For sync trees, if there are multiple paths that are equally good, then one best path from one node to the other is chosen at random. For example, H can be reached in 3 hoops via H, D, A, and B, as shown, or B, A, F, A, and D, not shown. This is simple and useful as there is a single route from each router to each destination. If instead all equally best paths are kept until the union is a DAG, okay, there is more general case that permits multiple paths from a router to a destination. The shortest path algorithm, JISCA, is the algorithm computes a sync tree on a graph. Each link is assigned a non-negative weight. Shortest path is only the lowest total weight and using the weights of 1. The algorithm, you start with the sync, set the distance at the nodes, relax the distance, pick the lowest distance, and then repeat. The notion of the weight generalizes distances to the other cost metrics. Setting weights to be 1 gives paths with fewer hoops. Setting weights to be distance gives paths that are shortest and lowest delay. Setting weights to be lower for higher capacity links favors at a higher capacity paths. Okay, so here's an example of the shortest algorithm. A network in the first 5 steps in computing the shortest paths from A to D. And the pink arrows show the sync tree so far. Okay. Here's an example of how it's actually computed. Okay. The first one is you start with the sync and all the other nodes are unreachable. Then you go to the relaxation step where the lower distance of the nodes link to the newest members. Okay. And then finally, you find the lowest distance added to the sync tree and then repeat it until the node. This code keeps going until it reaches a sought after destination node. If it continues until there will be no tentative nodes, then it would have found the entire sync tree. The predecessor links that to be reserved to find the path T to S instead of S to T. This is because the link has the same cost in each direction, so paths are symmetrical on the same each direction. And then of course, flooding. It's not like flooding your house, okay? Which is basically a simple method to send a packet to all the network nodes. Each node floods a new packet received on an incoming link by sending it out of the other links. Nodes keep track of the flooded packets to stop the flood, even using the hop limit that can flow exponentially. Note that flooding doesn't actually find any routes that can be reused. So it's basically like wasted material is just trying to be reused again. Distance vector routing, okay? Is distributed routing algorithm is the shortest path computational is split across all nodes, okay? And that is actually the diameter of the network is how long it actually takes to converge. Okay, in this figure, which is basically goes to the distance routing vector, is basically showing that the first 4 columns of part B show the delay vectors received from the neighbors of router J. A claims to have 12 mseconds delayed to B and 25 msec delays to C and 40 msecs delayed to D, and etc. Suppose that J has a measure or estimated its delay to its neighbors A, I, and H, and K as 8, 10, 12, and 6 milliseconds respectively. The count to the infinity problem. The setting of routes to best path across the network is called convergence. Distance vector routing is useful in a simple technique by which routers can collectively compute shortest paths, but it is also a serious drawback in practice, although it converges the correct answer and it may do so slowly. So in figure 5-10 on page 372, you actually can get an example where the delay metric is the number of hops. Suppose A is down actually and all the other routers know this. In other words, they all have recorded the delay of A as infinity. Link state routing. Link state is an alternative to distance vector. Okay? Distance vector routing was used with the ARPANET in 1979 when it was replaced by the link state routing. The primary problem that caused its demise was the algorithm often took too long to converge after the network topology change. Consequently, it was replaced by the entire new algorithm called the link state routing. Variants of the link state routing are called IS, IS, and OSPF, are the routing algorithms that are most widely used inside of large networks in the internet today. The idea behind this is fairly simple that it can be stated as follows. Okay? Discover its neighbors and learn their network addresses. Set the distance of the cost metric to each of its neighbors. Construct a packet telling all it has just learned. Send this packet to and receive packets from all other routers, and compute the shortest path to every other router. One of the informations needed for the exchange that has been collected is basically going to the link state packets. The packet starts with the identity of the sender followed by a sequence number of NH and then list of neighbors. As you can see, this is actually a figure on page 375 on your book, figure 15-12. It gives you an example that will shows the labels on the lines and the corresponding links state packets for all of the 6 routers as shown in that figure. Okay, in this other example, B has links to A and C and F in the network. It received LSPs from A, C, and F directly and so acknowledged A, C, and F respectively and sent that LSP on both other links. But B received E and D on 2 links, so it acknowledged both and sent only 1/3 of the link. Hierarchical routing is what you think it is to reach a given telephone first, head towards the right country, the right city in the country, and then the phone in the city. Each node keeps only 1 entry per region for other regions, plus an entry for all nodes in the local region. The advantages are smaller routing tables, smaller routing computational to run at nodes, and fewer smaller messages to send to describe the network. Broadcast routing. In some application, hosts need to send messages to many of other hosts. For example, a service distributing weather reports, stock market updates, or live radio programs might work best by sending to all machines and letting those that are interested to read the data. Sending a packet to other destinations simultaneously is called broadcasting. Various methods have been proposed for doing it. One broadcasting method that requires no special features from my network is for the source to simply send a distinct packet to each destination. Not only in the method wasteful of bandwidth and slow, but it also requires the source to have a complete list of all destinations. This method is not desirable in practice, even though it is widely applicable. Okay. In this example, you see that it requires only the regular unicast routing that is each node, such as built by distance vector. So it can be widely used. Sync trees are only available with a protocol that explicitly computes them to such a link state. Note that the broadcast with sync trees node, okay, to compute all sync trees, since the broadcast is forwarded by looking at the sync tree for the sources at each node, not a single broadcast tree for the network. As in the LAN spanning tree, however, using sync trees is more efficient since RPF oversends them. For example, D is reached from F going through the sync tree as well as G going out of the remaining links. Multicast routing. This example shows how multicast trees compute in the network. Okay, there are many more, the number of nodes times the number of groups. This is worth the effort when the group densely covers the network. Most groups affect most nodes in the network, so that it makes sense for our nodes to build efficient multicast tree. And you can actually refer to this diagram on page 384 of your book. Okay, on the figure 5-16, it actually gives you an explanation of how exactly this actually works. So for example, you consider the two groups, 1 and 2, in the network shown. The routers are attached to the hosts that belong to one or both of these groups, as indicated. A spanning tree of the left, most router is shown. This tree can be used for the broadcast, but it overkills the multicast as it can be seen from the two clone versions as shown next. Okay, all the links that do not lead to the host are members of the group 1 have been removed. Okay, this is another example. Okay, where for example here it shows the tree is the union of the paths that are actually placed on these packets. Okay, it is shown the core base tree for group 1 to send to this group as a sender sends the packet to the core. When the packet reaches the core, it is forwarded down to the tree. Okay, then from the sender on the right hand side of the network, as the performance optimization packet destined to the group do not need to reach the core before they are multicast. As soon as a packet reaches the tree, it can be forwarded up the route as well as shown on all the other branches. Okay, in this case from the sender at the top. So far they have covered several models. The next one is called a unicast, which is to all destinations, and the group of destinations is called a unicast, another delivery model, okay, that is sometimes also powerful. It is a packet that is delivered to the nearest member of the group. The schemes can be found called Anycast routing. Okay, and you can also find this on page 386 if you're following the book. Okay, and this procedure works because the routing protocol does not realize that there are multiple instances of destination 1 in this example. So it believes that all the instances of node 1 are the same node as the topology as shown in here. Routing for mobile host. Mobile hosts can be reached via a home agent. Fixed home agents tunnel packets to reach the mobile host, and they can reply to optimize the path. No changes to the routers or the fixed host. The trade-off is that is being made here is that the routing system that computes the spanning trees is not being changed at all, but routes to reach mobile host can be circuitous and to the mobile is far from home. So, millions of people use computers while on the go, from truly mobile situations with wireless devices and moving cars, to nomadic situations in which the laptop computers are used in a series of different locations. So, what it means by mobile host is a distinct from stationary host that never move. Increasingly, people want to stay connected wherever they want. So the model of the world that we would consider is one of which all the hosts are consumed to have a permanent home connection location that never changes. Each host also has a permanent home address that can be used to determine its home location. Analogous to the way the telephone number system indicates in the United States. You have, for example, the country code 1, Manhattan is 212. The routing goal is the system in which the mobile host is to make it possible to send the packets to mobile host using their fixed home address and then have packets efficiently reach to them wherever they may be. The trick, of course, is to find them. So the next one we're going to go over is called the ad hoc networks. Networks of nodes that just happen to be near each other and called ad hocs. Okay, so what makes an ad hoc different from wire networks in the topology that is suddenly tossed out the window? Nodes can come and go and appear in new places and drop at the drop of a bit. With a wire network, if a router has a valid path to some destination, that path continues to be valid, varying failures, which are hopefully rare. With an ad hoc network, the topology may be changing all the time, so the desirability and even the validity of the paths can be changed spontaneously without warning. Needless to say, these circumstances make routing in ad hoc networks more challenging than routing them in fixed counterpaths. If you're going through the book as well, on page 390, this example is actually listed there, okay, on figure 5-20, and it actually describes the algorithm, okay, where you suppose that process A node wants to send a packet to node I. The AODB algorithm, which is the ad hoc, maintains the distance vector table at each node, keyed in the destination, giving information about that destination, including the neighbor to which to send packets to reach the destination. First, A looks in its table and does not find an entry for I. It now has to discover a route to I. This property of discovering routes only when they are needed and what makes this algorithm on demand. Congestion control. Yes, it's not traffic congestion, but trust me. Okay? Handling congestion is the responsibility of the network and the transport layers that are working together. So they look at traffic, admission, traffic, throttling, and load shedding. So traffic aware. Okay. Congestion results in too much traffic that is actually offer performance degrades due to the loss and retransmissions of good put. I'm on page 395 right now. As offer load increases, the good put should increase correspondingly until the capacity of the network is reached. Good put will trail offered load because the load is bursty and queues will occasionally be too full and a packet will be discarded inside the network. Congestion collapse and occur if the protocols are not carefully designed when the nodes retransmit the packets many times believing that they have been lost. When copies of the packet are still in the network pending delivery, while throughput it is a receiver that may be high, good put falls because multiple copies of the same packet are being received after the first copy of the bandwidth is wasted. Okay, this really happened in the late 1990s when the internet grew, and it led to the design of the modern TCP that included congestion control mechanisms. So congestion control, the approaches. The network must do its best to offer the load. Provisioning is simply sizing the network to fit the offer load. Don't build it too small or with little west to east capacity if there is much west to east traffic. So in other words, if you know you're going to have a lot of traffic, don't build it too small. Traffic-aware routing. As previously routes only considered topology, this approach can get more traffic through the network. If not careful, then routing can notice CF is busy and switch traffic over to IE, only to later notice that IE is busy and switch traffic back to CF. These are various techniques to avoid. Number one, change the routes only slowly. Traffic engineers in which an external system sets weights in on the routing system does not otherwise adapt, and using multiple paths at once, both CF and IE at the same time. So how can networks be connected? Inner networking. The top half of the figure shows the difficulties. A packet sent as a datagram may suddenly have to be sent over a virtual circuit, which requires some way of map between the two. The bottom half shows the solution where a common network layer protocol IP carries the address and then the other information that identifies the endpoint across the network. Famous tunneling. Okay, you can actually tunnel in. It connects the two networks through a middle one, and the packets are encapsulated over the middle packet. Basically, it's encrypted, where you may have one router in the East Coast, one around the West Coast, and you're going through a tunnel, which is basically like an invisible connection that actually flows through there, and all the data is actually encrypted. Okay? The analogy is that it's a link. The packets can only enter and exit at the end. So in between, you don't know what's going on. As you can see, you're going underwater in this example. Fragmentation. Networks that have different packet size limits the many reasons. Large packets send with fragmentation and reassembly. So this process basically is, it actually allows the routers to break up the packets into fragments and then sending each fragment as a separate network layer packet. Okay, this sometimes helps with the process as well to transmit all of these packets. As you can see, there's an example there, and if you can actually follow me on page 434, it gives you a more detailed example of actually how this process works. Okay, so here's actually another example also. This is figure 5-43 on your book as well. Okay, and it actually gives you some ideas and an explanation as how a simple design that has attractive properties. So fragments can be placed in a buffer at the destination in the right place for assembly, even if they arrive out of order. Fragments can also be fragmented if they pass over the network with a yet smaller fragmentation. So you got the original packet, the fragmented package, and the refragmented package, right? But still, it's going to go all through. So here's another example where you actually have the path MTU. The discovery avoids the network fragmentation. Okay. So now we look at the network layers. We're going to be looking here at IP version 4 and IP version 6. Okay. Again, if you are actually following me, this actually starts on page 436 on your book. Okay. So the network layer is basically the internet. The IP has been shaped by guiding principles by making sure it works, simple, clear choices, avoid static options, strict sending, and so on. Very much an open working design that has favored simplicity and practical engineering considerations rather than a design by committee. So here's an example here of how the network layer and the internet actually work together, and this is actually on page 438 of your book. Okay, so this actually gives you just basically an idea of how a packet originating at a host at a home network has to traverse 4 networks and a large number of IP routers before even getting to the company network in which the destination is actually hosted. As you can tell right here, how it actually travels from one place to the other. It's kind of like you're going through state to state to state to actually get into where you want to go and going through all those highways. Okay, So we look at IP version 4, which is actually right now one of the most popular ones that are actually used nowadays, okay? And basically what it is the network is actually the internet in which the format of the IP diagrams itself. IPv4 diagram consists of the header part and the body and or payload part. The header has 20 byte fixed parts and its variable length option part. The header format is shown in this picture right here, and the bits are transmitted from the left to the right and the top to the bottom, with the high order bit of the versions field going first. This is a big Indian network byte order on a little Indian machine, such as like for example an Intel x86. Okay, it also, for example, IP addresses also have subnets, okay? And subnets are basically different networks, okay? And if you have actually done your Cisco certifications, you will definitely have heard about subnets, okay? So the solution is to allow a block of addresses to be split into several parts of the internal use as a multiple network, while still acting like a single network on the outside world. This is actually called subnetting, and the networks such as Ethernets the result from dividing up a larger network are called subnets, as we mentioned earlier. You should be aware that this new usage of term conflict with older usage of subnet to mean to set other routers and communication lines in a network. Okay? If you want to actually look more in detail, you can look on page 445 and it gives you a clear view of how the subnetting actually works. And then of course you got NATed. NATed actually is like, for example, whenever you're at home and you're trying to have your own system, okay, is your internal network that is actually not visible, does not have an IP address, they're all IP internal addresses. Okay, so for example, here you can tell that you actually have your router, which is your internet service provider, and then you actually have a translation of packets that goes into a private address as shown in here, and that's your translation, which is basically inside, and it's called a network address translation. And then we move into the IP version 6. Okay, this is actually a new version that some companies are using, some are not using yet. Okay, but basically it has been used a while, but actually has been built for a while, but hasn't been used. Unfortunately, the IP has become a victim of its own popularity, and it's actually running out of addresses. So for IPv6 is the answer to everything. So the last IPv4 addresses are expected to be assigned by the ICANN before the end of 2012, which happened already. Okay, so IPv6 is the replacement design that does just that. It uses 128-bit addresses. Okay, it addresses a shortage of these addresses is not likely at any time of the foreseeable future. However, IPv6 has proved to be very difficult to deploy. It is a different network layer protocol that does not really interwork with IPv4 despite many similarities. Also, companies and users are not really sure why they should want to have IPv6 instead. So there are still some issues with IPv6 as shown in here. We're trying to work with this. And as you can tell here, this is 128 bits versus a 32-bit from an IPv4. Okay. The IPv6 extension headers handle other functionalities as well. For example, you have fragmentation, authentication, security, routing, destination, and hop-by-hop options. Internet protocols, for example, with the IP, you got ICMP, ARPF, and DHCP. DHCP is actually one of the most popular one that assigns a local IP address to a host automatically. That's basically like getting an address, like for example, whenever you're at home. The Internet Connect message protocol types, you can tell here as well, and you may also look into that on page 461, okay, through 467. That's where actually more detail can be explained on all of this. Again, this lecture covers one of the most important parts of this chapter, but does not cover it as a whole. Your job is also to make sure that you actually read the chapter, okay, and make sure that you actually understand it. If you have any questions, of course, you may ask the instructor. And please make sure to do your homework and your discussions. Thank you.